Good afternoon, Girl Scouts. How are we doing today? Good. Are you excited about your 100th anniversary sing-along tomorrow? Where we are excited to be at the mall and watch you. And today we are thrilled to have you here at NASA as you rock NASA. Are you excited? Yes. Yeah. Well, we're excited to tell you all about science, technology, engineering, and math, and we have a lineup of really cool women to speak to you. We're going to start off with our Deputy Administrator. That puts her second in command at NASA. Miss Lori Garver hails to us from Michigan, and she has degrees in political science, economics, and science and technology policy. But most importantly, this is the coolest part, she was a Girl Scout herself. So we're very excited. We're very excited to have Miss Lori Garver.
Thank you so much. Good afternoon. It is wonderful to have you here at NASA headquarters. We congratulate you on your 100th year anniversary and welcome you to Washington and to NASA. So I was indeed a Girl Scout many years ago, and there's no question that being a Scout shaped me and taught me things that continue to help me in my job today. The organization, the Girl Scouts, strives to teach girls self-reliance and resourcefulness. It also encourages girls to seek fulfillment in the professional world and to become active citizens in their communities. That's what it says when I looked it up on the web. So in my experience, there are no better skills than those to prepare you for the future. You are learning a sense of adventure in scouting and how to serve the world you live in. And when you look back at the 1929 Girl Scout Handbook, it says that the Girl Scouts were named after the explorers of the West. The most resourceful and hardy and experienced of that number went ahead to find the best way for the others to follow. They were called the Scouts of the expedition. They had to have courage and perseverance and endurance and an understanding of the ways of the animals and plants, of the meaning of the winds and the water and the lay of the land. Their success meant success of those who followed, and they made the best traits through the land. Adventure was theirs, and the joy of accomplishment and the satisfaction of service to others. This is from the 1929 Girl Scout Handbook. So it would have been pretty hard for them to see that the winds and water of the explorers of their day have now turned into explorers in space, and the solar winds and looking for water on Mars. But that is what those of us who were Scouts are growing up to do. And that pioneering spirit continues on the frontier of space, I would say, as it did in the West, and we tap that same spirit of courage and perseverance and adventure to explore now not just the land, but also air and space, and that's what we're doing here at NASA. So I think we would all agree that brave and adventurous are words we would like to describe ourselves as, right? It's one of the things you learn in Scouts. I would add a word that has been something that has been described about me for a while, which is determination. So when I was your age and my class in church was getting confirmed, you had to leave the confirmation class, which was maybe 20 or so of your friends, while they each came up with a word that would describe you, that you would find out that word in front of the whole congregation on Confirmation Sunday. And I went off and my friends picked my word, and of course when they were all out, we picked words for them: courteous, friendly, bright, wonderful, wonderful words. But on Scouts, this was on Scouts Sunday, on church confirmation, when they came to me and I was a 12-year-old girl, the minister says that the word that was chosen about me was determined. Well, you can imagine, 12-year-old girl, that was not the word I was truly looking for at the time. I think since then I have grown to embrace that even at the age of 12, people could see my determination, and I would encourage you all girls to embrace your determination and your spirit. while I'm giving advice, I'll share another quality that I think pioneers need, and you're hopefully learning in Scouts, and that is assertiveness. Hopefully we'll get into this in the Q&A. You can all be assertive and ask me absolutely anything you want, and I will try to answer. It doesn't mean you're not polite, but I do believe that we, as girls and even adult as women, can be more assertive. I was speaking this morning to Career Day High School in McLean, Virginia, where my youngest son is a junior in high school. My other graduated from there. I only have sons, so this is a special honor to me to address girls. I'm very jealous of my friends who have girls, but the message that I even gave to boys and girls in high school career day this morning is to be willing to always try something new, ask questions, and learn from your experience and move on. Charlie Bolden, the head of NASA, has something he says a lot, which is he never learned from something he did right. So if you have done something wrong, just learn from it and move on. So just as the Girl Scout founders could not have imagined our life today, we can't imagine the opportunities that you're all going to have in your lives. In the space field alone, you will be able to help us invent things like new vaccines by doing research in the microgravity environment of the International Space Station. You will be able to discover new Earth-like planets rotating around distant stars through things like using our Kepler observatory, or the to-be-launched in a couple years Webb Space Telescope. You could also help millions of people have access to fresh water by studying our own planet as we do from satellites from space. You could also have the chance, of course, to be a pioneer and travel to an asteroid or walk on Mars. And while we don't know exactly what the future holds for NASA, we know it is bright. We have our vision to reach for new heights and reveal the unknown so that what we do and learn will benefit all humankind. So what better vision can we have than doing the new thing, the hard thing, pushing back the frontiers of air and space, not just because we want to, but to benefit humankind. So we do this through aeronautics research and helping to make commercial aviation safer, more fuel efficient, quieter, and more environmentally friendly. A lot of you flew here today, so you'll have an interest in making that happen. We study the Earth, as I mentioned, from space, our home planet. Currently, we have 16 operational spacecraft looking at things like water salinity and temperature, how we are able to understand the change that is happening to our planet so that we can better prepare for the future. Space science in astrophysics, heliophysics, and planetary science. We have rovers on Mars as we speak. We have the Curiosity rover on our way to Mars to land on August 5th, the size of a car, to help us learn new things about that interesting planet. We have spacecraft operating right now around the Moon, Mercury, Mars, Saturn, and one on its way to Pluto, and another to Jupiter. And in human spaceflight, we have the International Space Station with 6 astronauts and cosmonauts aboard as we speak, doing science aboard the station to help understand how we can go further and how to make life better here at home. The International Space Station is our foothold to the future, and we believe that, again, we can go beyond low Earth orbit. You know, we've been to the Moon 6 times, but the President has laid out that we'll be going to an asteroid for the first time in around 2025 and on to Mars for the first time in the 2030s. So NASA is often associated with astronauts, and for good reason. They've done incredible things. So, in fact, you'll be hearing from one of NASA's finest astronauts just this afternoon, Pam Melroy. Earlier this year, we started the process of recruiting for the next astronaut class, and these people will be flying to the International Space Station. As you know, we retired the space shuttle, but we are developing new rockets and new spacecraft to go to space NASA is developing the Orion spacecraft on the heavy launch vehicle to go on the asteroid and Mars missions that I mentioned. And we're also partnering with the aerospace industry and private industry in order to be able to have more opportunities for people to go to space and reduce the cost of transportation. So you might have seen last week we had the Dragon capsule dock with the International Space Station and deliver cargo back here from the space station. So we have a very bright future at NASA. So there are a number of women besides our astronauts. We've had 43 astronauts who are women go to space with NASA. How many people do you think have gone to space if 43 are women? 500. So I think there's 53 women total who've gone to space, 43 Americans with our program. So are we 10% of the population, ladies? No. No, it turns out we're over 50% of the population. So March was Women's History Month, and I gave a lot of talks about girls and women and going into the sciences and STEM fields, science, technology, engineering, and math. And we've made a lot of progress. When I was your age, no American women had gone to space. Sally Ride went to space while I was in college, which was a big inspiration for me. And NASA employs scientists and engineers across many fields, but only 22% of those are women. We have some stellar examples, not only those 43 astronauts, but the principal investigator now on our lunar mission Grail and on our New Star mission are female. Our CFO, Beth Robinson, is a female. Our head of, our chief information officer, head of human relations. We have a lot of examples of women going into these fields. But one of the things I hope we can talk about in the Q&A is the kinds of things that excite you and what you want to go into with your careers. So during Women's History Month, when I got asked to talk about this, a lot of people asked, why is it that girls and young women are not going into these fields at equal rates from boys and men? And my general field, my general view that I have been sharing is along the lines of that women have a tendency to want to go into fields where they can see a direct benefit or where their work can help make the world a better place and make a difference. And we haven't really sold what we do in NASA in this way in the past. We've sold it on things like, you know, making a rocket. It's something that we love to do is, you know, let's go light the candle, let's fire up the rocket. And that can be fun. And believe me, going to something like a space launch is a lot of fun. But it's about a lot more than that. It's about more than rocket science. It's about, as I said with our vision, right, learning new things, new knowledge, discovering ways we can make life better here on Earth. So while I've speculated that these are some of the reasons, I was very interested last evening to find out from my deputy for policy, Rebecca Kaiser, who's here in the front row, that the Girl Scouts just did this research on why there aren't more women and girls going into STEM fields and put out a report in March. Their data show that 74% of high school girls across the country are interested in the fields and subjects of STEM, but in fact, very high percentages of those go into the health and medical sciences for precisely the reasons I think I was speculating. It says that girls are interested in the process of learning, of asking questions, and problem solving. So those are all science and engineering kinds of questions. Girls want to help people and to make a difference in the world. They're interested in many subjects, not just STEM. So while I think we have the opportunity for more girls to go into science and engineering, when we end up explaining what we're doing in a way that doesn't really connect to helping people and making a difference, I think we lose some of the interested girls. So it says that girls in STEM want to understand how things work, solve problems, and do hands-on activities. So the study concludes that 2/3 of STEM girls go into medicine and healthcare careers such as doctors, veterinarians, nurse, and pharmacists. We tend to think of these as the soft sciences and engineering and the hard sciences being more male-oriented. So I would love, again, in the Q&A to see what excites you and if some of these statistics are in fact correct. So when I was going to be talking to you today, I sent my mom an email last night because not only was I a Girl Scout, but my mom was a Girl Scout leader. And as I looked at my schedule today and I saw that I would be here with Girl Scouts celebrating the 100th anniversary, I sent her an email. She's 81, still lives in Michigan, and said, Mom, I'm talking to the Girl Scouts on their 100th anniversary. Do you have any memories of Scouts that you would want me to share? And I got the following email from her that I want to read to you just about an hour ago, and it's really probably going to be of more interest to the leaders among you. She says, Dear Lori, thanks for asking me about my memories of you as a Girl Scout. The sash that you wore over your shoulder that we sewed all the badges on is still full of badges and hanging in your room here in Michigan, and I have seen it there whenever I go. I remember you being enthused about earning the badges and doing all the requirements specified. And my 81-year-old mother literally writes in parens, unlike Renee Cisco, who wanted the badge, didn't do the work. I know, isn't this hilarious? And Irma always gave her the badge anyway. Okay, so Irma was my mom's co-leader, and we are hoping Irma and Renee Cisco are not gonna watch this. You always liked camping the most, and I remember taking the troop to Wacusta near Grand Ledge along the river. We cooked over a fire and slept in tents. When it rained, you never seemed to mind a bit. You went to lots of other camps too with more Scouts up north. Leading was a good experience for me, especially with Kay. So this is her friend Kay. When Kay moved and Irma came, not so much. I liked it. So it's really good if you have, I'm sure you know this because I helped with my son's Scouts too, that doing it with a friend is always better. I liked getting to know the other girls that weren't your friends, some of them who had fewer opportunities than you did. I wish I could remember their names so we could look them up on Facebook and see what they're doing. I think about them often and hope being a Girl Scout gave them some opportunities they wouldn't have had otherwise. I knew that was going to happen. Okay, so it says, she says, the leaders were well organized, so take that, leaders, and I had to be in charge of cookie sales, which was the biggest job. Is that still the biggest job? It sounds like it. I know for the Boy Scouts it's popcorn sales, but Girl Scout cookies are probably the interaction that most public has with Girl Scouts. I met other interesting women in the community, some of whom I still see occasionally. About 5 years ago, driving back from Florida, we stopped in Savannah to go through the childhood home of Juliette Lowe, founder of the Girl Scouts. I think she would be proud of what she started. Oh my gosh. Okay, so I'm sure your speech will be fun to hear for the Scouts today. And could you please send me a copy, though, Mom? So, a special shout out to you Scout leaders who I know I did not fully appreciate my mom when she was my leader. So, just this last week, as a matter of fact, it was my honor to be at the White House when President Obama presented the Presidential Medals of Freedom. I'm sure you guys heard about this, but the Medal of Freedom is the nation's highest civilian honor, and it is presented to individuals who have made especially meritorious contributions to the security or national interests of the United States, to world peace, or to cultural or other significant public or private endeavors. So John Glenn was receiving the medal, and that's why I was there to be present when he received it. So was Madeleine Albright, former Secretary of State. So Hillary Clinton was there with her. Bob Dylan received one, and so did founder of the Girl Scouts, Juliette Lowe, posthumously. So great, great history of this organization. So it's an honor to be here and talk to your Scouts today. I hope that some of you will in fact choose to work at NASA in the future, but I mostly hope that You will build on your scouting years to lead fulfilling and productive lives. And I wish you the best success in any career you choose. And I really will be willing to answer any questions that you have. Thank you for being at NASA. So, I'm going to come around because I'm going to be Oprah. She doesn't do it anymore, so someone has to. They mic me up, so hopefully you can still hear, because I think you might be more willing to ask questions if I'm down here. Any questions about NASA, Washington? Oh, go ahead.
What were your interests when you were younger, junior high, high school?
My interests when I was younger, probably not unlike most of yours. As I said to the kids at Langley High School today, my son's school, I would have told you, I think, when I was your age, that I wanted to be an architect. You truly do not have to know what it is you're going to do, or even what you want. So I did have an interest in math and science, but I did not go into math and science and major in them in college. I majored in political science and economics, namely because I think I did feel that those were areas where I could make a contribution. My grandfather and uncle were, well, farmers in Michigan, also in the state legislature and state senate, and for a political office like that, it's almost a volunteer activity, it's part-time. But they really instilled in me that public service is something that can make the world a better place, and that you should really do that. So I didn't set out to work at NASA. I came to work here in the 90s after working for John Glenn. My first experience in Washington was working for John Glenn, so it was really fun to be with him last week when he got the Medal of Freedom. But for me, I came about it more from a public service aspect than a science and math aspect. Right here.
How did you get started working at NASA?
So I worked for John Glenn when he ran for president. So this was 1983 and 1984. None of you were born. And he was running for president at a time when Ronald Reagan was president. So when I was in college, I had gone around the world in mainly to a lot of third world countries. And it seemed to me that we in the United States could do a better job of helping people all over the world. And so I moved to Washington in order to try and do that. And I thought John Glenn had a really good chance of beating Reagan in that second term. Well, it didn't happen. In fact, my political science picks have not all won, but you know, that's that perseverance and determination. And because I worked for John Glenn, I got to know a lot of people who work for NASA, and I started to learn more about the value of what we do in space. So as I looked at that, I was choosing a graduate school program, and I went to GW, George Washington University, in Science, Technology, Public Policy, and that really helped me to decide that where I should have my career was in helping the space program really contribute to sort of public value better. And I worked at the National Space Society for 14 years. I was the executive director of the National Space Society, but I started as a secretary receptionist. And I worked my way up at that organization. I remember in my interview for secretary receptionist, the guy who was head of it said, you know, if you stick with this, there's a lot of opportunity. In 10 years, you could have my job. Well, you don't have to know a lot about me to know what I was thinking at the time. Not going to take me that long. And it didn't. 4 years later, he retired. I was executive director, and I worked there for another 9 years. And during that time was testifying before Congress on the value of the space program, and was supporting NASA outside of NASA as a member of the public. So at that time, the head of NASA, his name was Dan Golden, he literally called me up one day. It's one of those moments you'll always remember, and asked if I would come work for him at NASA. So it was having worked for John Glenn, having decided it was a path I wanted to follow, getting an advanced degree in it, and then working so hard in it that people who were at senior levels recognized what you could contribute and hired me to be here. Now, this time I'm at NASA, though, was even more fun because I was working for Hillary Clinton on her presidential campaign. And I was volunteer and helping with her space policy. So when she got out of the race and President Obama was our nominee, his campaign asked if I would come do the same for him, and I was happy to do it. So when he won the election to be president, he asked if I would lead the transition team for NASA. So during the time when the election is held and when the inauguration takes place, you have about 3 months where each agency gets a team in to help understand what's happening with that organization and make recommendations for what they should do under the new president. And so I got to lead that transition team at NASA this time for President Obama. So he nominated me to be the Deputy Administrator, and I was confirmed by the United States Senate. There are only 3 jobs at NASA that are like that. The head of NASA, Charlie Bolden, who I mentioned, my boss, he's flown in space 4 times. He's a 2-star Marine general. And you know, you can imagine that is extremely exciting to work for him. And then our CFO, who I mentioned, Beth Robinson, another fabulous strong woman who has a PhD in physics. So it's a great team at NASA, and again, I couldn't have chosen, said this is what I'm going to do, but I think as long as you're doing something that you love, it's going to show and you're going to do a good job at it. Back here?
Did you always like your job?
Did I always like my job? Of course not. It's a job. As I've told my kids who have summer jobs and don't love them, there's a reason they pay you. You know, otherwise we just do it. I would say, you know, I've had, even in this job, you have good and bad days. But I think I have always enjoyed the aspect, certainly the last 25 years it's been in the space field. So there's one of the things I like about it is there's always something new to learn and do. And to me, that keeps it exciting. The days don't drag. But I worked at McDonald's when I was 16 years old. I actually sort of think I love that. The free food was a real highlight. I've taught aerobics. I have had interesting jobs like everybody else. I was an aerospace consultant for the 8 years during the Bush administration, between times I worked at NASA. And there are aspects of that aren't as much fun as this job, but so no. If you're having a day that's not so great, don't worry about it. Or if you're in a job sometimes that you don't love. So I have 2 kids, and one of the difficulties, of course, as women is to balance having kids and a full-time job. And so as I have counseled women who work here at NASA, maybe are going through that, I got advice from a friend's mom once that said, you can have it all, but probably not all at the same time. So when I had little kids, my job wasn't as demanding as it is now. And now my oldest is in college. My younger one, as I mentioned, is just going into a senior year in high school, and they don't really want me around anyway. So a good thing is, because of this job, they actually are interested in what I do, and I think that's helpful too. Yes?
Do you think that any of the skills that you learned in Girl Scouts help you in your job today?
Yes, as I mentioned, and I would say I didn't really appreciate this fully until I thought about what I was going to say to you guys today, and as I read what the Girl Scouts are about, and the fact that, you know, we as Scouts, I didn't really appreciate, we're the frontiers women, right? And I'm sure you still do a lot of camping and develop those individual skills that make you just want to understand something you didn't know about before and ask a question you didn't know about before. That's what I do every single day, not out in the wilderness, but up in space. And I'm not personally in space, but hopefully I will be someday. The ability, I think, also to be a leader within a group in the Scouts is important, to work with your fellow Scouts, to do things like the cookie sales. They probably don't encourage you to go door to door, but I can remember going door to door selling Girl Scout cookies, and I see you all now at malls doing that. You're developing life skills, and the badges that you have, I can't actually see what you've learned to do, but those badges, unless you're Renee Cisco, are all about learning a skill, right? Oh gosh, I couldn't believe she wrote that. So yes, absolutely. Stuff you're learning now is going to be helpful no matter what you decide to do. Yes?
Earlier today you talked about how the girls want to do something that they actually give back to and help people. Can you go ahead and explain some of the spin-offs NASA has, for example, like the digital mammogram, that help people?
Sure. So I do mention that a lot, that NASA, the investment in NASA ultimately helps a lot of people. And there are things from direct benefits, like I talked about, looking at the Earth from space and being able to track weather patterns that will save thousands of lives and those kind of things. But there are also things, like was just mentioned, called spin-offs. So maybe NASA, we're investing in something called the Hubble Space Telescope years ago, and we developed an imaging capability that helps you look into the universe and determine star clusters and quasars and pulsars. Well, guess what else that technology helps you do? So it helps you have a better mammogram that can detect breast cancer earlier and help more people survive. So that is one of thousands of spin-off benefits of the investment in NASA technology. I also mentioned benefits like studying how we can make new vaccines in space. So that is more a direct, we're investing in this. We have a couple of companies, including the National Institutes of Health, who are doing this with us in space, and you could develop the cancer vaccine. There are spin-off technologies relating to materials we have developed that are helping technologies here from medical to environmental fields. And so NASA is less than 0.5% of the federal budget of your tax dollar, and it truly is an investment not just in what we're actually doing and benefiting through new knowledge and studying the Earth and space, but also in things like spin-offs. So we really, really believe that investment is worthwhile. Yes?
What sort of classes did you take in college that have helped you get to where you're at now?
So in college, I majored in political science and economics that really did help me understand how democracy works in this country and how capitalism works in this country. And so I work for the public right now that is absolutely based on things I learned back then. I learned that we have a great system of democracy in the United States. It is something that we should all be proud of and we shouldn't take for granted. We have seen just in the last couple years other countries struggling to gain such a democracy, and I think the U.S. is an amazing symbol of that. In addition, our economy, while we're going through difficult times right now, is a capitalist economy that recognizes as we invest our government tax dollar in things like NASA, those technologies and investments are taken by the private sector to create all kinds of new advancements. And so in my job today, I use that basic knowledge and skill that I learned in college every single day. Since I wasn't a science and engineering major, those aren't particular areas of science that I use in my job, and I am extremely lucky that, so NASA has 18,000 people, about 70% of which are in science and engineering fields. Those people are very good at explaining their science and their engineering, and so I would say I also learned in college how to listen, how to learn, how to understand, how to communicate, and those skills you need every day. So even if I were, say, an aeronautical engineer, I wouldn't necessarily understand when the folks come in and tell me how they're doing on the Webb telescope and how astrophysics is being developed. So you really have to, I believe, I'm a pretty big fan of learning to think and learning to make logical sort of decisions. I think engineers are particularly good at that, and we have a lot of those at NASA, but I think you learn those skills almost no matter what you study. So it really is, I know you probably hear this a lot, studying something, focusing on something that you enjoy and are good at, because you're going to enjoy that even more and make a contribution. Yes?
Why did you want this job?
Why did I want this job? I almost never get that question. So, as I mentioned, I've sort of had this life goal since very early after college to make the world a better place, and I feel like NASA is doing that every day. So helping NASA do that better and help communicate to the public and to our elected leadership how we're doing that so that it gets more support, sort of a life goal. And there's only a handful of jobs that you get to do that in the whole world. And I often say I have the best job in the world, because that is really what I'm doing on. And I've grown up wanting to do it. And I don't think you get the opportunity very much to do exactly what you wanted. But I couldn't have told you this is what I want to do. I didn't even know, really that it would have existed. So all kinds of careers are going to exist out there for you that you don't even know of today. There's some statistic like 70% of the jobs that you will have haven't even been invented yet. I'm sure that's true. And as the technologies advance, it opens up opportunities that we don't even know of today. So I would, as I mentioned, keep as many options open and be really open to new things and ideas as you can.
Thank you so much,
okay.
Lori. That's it.
Thank you guys very much. Enjoy your week and
So as I'm sure you notice, one of our fearless leaders is very passionate. She is emblematic of what many of us consider, as she said, determined and assertive. So we're very fortunate to have had her speak to you. Next, we have a scientist. She's an astrobiologist and a mineralogist at NASA's Goddard Space Flight Center, which is just up the road from D.C. in Maryland. And we are very fortunate that she will be able to speak to us. And you'll also learn from her that she is a passionate Girl Scout. So if you will please help me welcome Dr. Pam Conrad.
So I am so disappointed to be talking to the Girl Scouts. Not. I can't join you for Rock the Mall tomorrow. My mom just got will be getting out of the hospital tomorrow. She now has a bionic hip. And she just used it for the first time today to walk up and down some stairs. So I need to go spend some time with Mom tomorrow. And by the way, she actually is also a leader. She was my sister's Brownie Troop leader. And so what I want to talk to you about today is all the cool things I get to do. And many of them I learned to do as a Girl Scout. But one of the coolest things I learned how to do was learn how to play the guitar and sing. And since I don't have a guitar here, and I don't get to go to Rock the Mall tomorrow, if you will just indulge me and sing with me one verse. Girl Scouts together, that is our song. Who's singing? Winding the old trails, rocky and long, learning our motto, living our creed, Girl Scouts together in every good deed. Man, you all sing so softly. And by the way, this one's mine. Okay, I have a few things I'm going to show you, and I have a little movie that I'm going to show you, and then I want to spend just a couple minutes talking about what I do and tell you how it relates to what I did as a Girl Scout. So the first thing that I learned as a Girl Scout is how to make a tent that did not sag. And that's especially important when it's raining. The second thing I learned how to do in Girl Scouts, I just told you, and that was how to sing and play the guitar. The third thing I learned how to do as a Girl Scout is now what I get paid to do all the time, which is to be an explorer. And I want to teach you how you can be an explorer too. Because no matter what job you hold, you can always be an explorer. So if we could have my first slide, please. The most important thing I want to give you is my email address. So if you have questions, you can write to me, and I promise you I'll answer you. It's down at the bottom there, and it's kind of not very bright. Can we dim the lights just a tiny bit so that they can see the email address? Anybody who can write really fast, it's pamela.g.conrad@nasa.gov. Okay, next slide, please. Now, you all know how I feel about the Girl Scouts already. We discussed that. And the Girl Scouts teach you lots of good stuff. Can I have the next slide? The Girl Scouts taught me how to explore, how to camp. And let me tell you something. When you're camping on the polar plateau in Antarctica, it's really cold. And especially if you're camping with 8 guys, they whine a lot. Whine. So I picked one of them to be the cook. When you're camping in Antarctica, you have to be very careful. A lot of it is a protected area, and you have to take out everything that you brought in with you, including things like your pee and your poo. So one of the things a principal investigator has to do with a big mission like that is I have to calculate how many poo barrels it takes for 9 people camping 1 month. So math is important because you don't want to be short on the number of poo barrels. I still have that Girl Scout flag, that's me. And I also have another little Girl Scout flag that I have taken with me when I got to go in a deep sea submarine and explore the very bottom of the Pacific Ocean. Could I have the next slide, please? This is a painting, right? Not. This is a photo of Llewellyn Glacier, which is in the Northwest Territory of Canada. It's an amazing place. You see how that snow looks kind of dirty, brownish, reddish? Those are all organisms that live in ice, microbes that live in ice. It's a type of algae. It's called snow algae. And I went up to Llewellyn Glacier to try to understand how living things can do it there, what they need aside from the water. It's mighty cold, but it was just so gorgeous. I had to take that picture. Next slide, please. So let's talk about exploration a little bit. Why do you think we explore? Think about it a little bit, and we'll talk about it in a minute. What value do we get for exploration? I mean, what do you really get out of it except for the fact that it's kind of fun? How do you make it happen? I told you everybody could be an explorer, and I want to make sure you know that you can too. And how can you start, like, right this minute? Next slide, please. So, next slide. Adventure. Adventure is when you go do something really cool and it kind of gives you a thrill, and there's lots of adventures. You know, it could be like surfing, that's pretty cool, or sailing, or horseback riding, or rock climbing, or all kinds of stuff. Next slide, please. Exploration is different. Adventure is something that humans choose to do. And there are not very many animals that have adventures, but all animals explore because the purpose of exploration is to understand your environment, to reach out and touch a little piece of your environment so you can figure out if it has food for you, if it holds danger for you. Every living thing explores. It is the destiny of every organism to explore. Could we have the next slide? Science. As in big science. So, what is the purpose of science in this list? Science is what you do as a technique when you're exploring to make that exploration valuable to more people than just you. It's a method. It's a technique. So if you use science when you explore, it teaches you how to make value for your friends and your family and the rest of humankind. Next slide, please. So you can explore at every kind of size scale. You can get out a microscope and you can look at the tiniest little microbe. You could get out the biggest telescope and you can look at scores of galaxies. And that is the whole totality of all the sizes that you can and should explore. And the reason why is because some things are important at one size scale and some things are important at another size scale. And it's always important to hold the big picture in mind so you can figure out the meaning of something. Just looking at one thing sometimes doesn't tell you the meaning of it. Keep the big picture in mind. Next slide, please. This is called Battleship Promontory, looking down into a valley in Antarctica. You see how the rocks in the foreground are kind of that tan color? They got a little snow on them, but you can see they're a different color than the rocks down in that valley, right? That's because the rocks down in the valley are made out of something else. Here's what's really cool. You can look at things sometimes and just learn something about them by a quick glance. Those rocks are darker. The rocks in the foreground have multiple colors on them. The reason why the rocks in the foreground have multiple colors on them is because there are microbes that live inside those rocks, and they actually breathe metal. They breathe in iron, and they exhale iron, and when they exhale the iron, it's changed to a different color because the chemistry is different. If you're a smarty pants and you know a little about chemistry, you'll know that when you have an extra electron, you're negative, and when you have one electron too few, you're positive. So that's what these guys do. These microbes, they take electrons, they give away electrons, and they basically breathe iron. Where do they get the iron? Those dark rocks at the bottom of the valley are made out of iron, and when they get weathered, it becomes dust, and it lands on these light rocks in the foreground, and it provides iron so that the bugs that live in the rocks can breathe the iron. And that changes the color, and when iron changes color, what do we call that? Anyone know? Rust. And oddly enough, it kind of looks sort of like a rusty color, doesn't it? Next slide, please. So this is, at the other end of the globe, this is the Arctic. And that's me in the blue sweater. And you see that tiny ship down there in the fjord? You see that ship? We hiked up to the top of this volcano from all the way down there. We took a little rubber boat called a Zodiac to the shore, and then we hiked up that volcano. And that big rock that is just to my right, we were exploring that rock because it has minerals in it that are exactly, and I mean exactly, like some minerals that we have found in meteorites that come from Mars. More on Mars in just a second. Next slide, please. There's the ship up close. That's where we live when we're exploring the Arctic. It's really pretty cool. And we see a lot of polar bears, so every time we see a white dot, if it's moving, we make sure to head back to the boat. They eat people. Okay, next slide, please. So what I do is I study habitability, which is a little difficult to say. But habitability is how livable is an environment. We want to understand what makes some planets livable and other planets not. I would say that this one's pretty livable, right? I mean, we have Girl Scouts, we have cookies, we have ice cream. It's a good planet. But not every planet feels so good for us. And it's not to say it might not be a good planet for somebody else. But so what I do is I try to understand what makes an environment habitable or not. And that means you have to think about for whom it might be habitable. Now, when we try to figure out how to do this, we have to figure out how to measure this. Because as scientists, we can't just say, oh, this is pretty cool or that's pretty cool. We have to measure because science measures. And by the meaning of our measurements, we determine the answer. So I want to tie
what my exploration in various environments does when I use science. And when I use science and exploration to learn about if an environment is habitable or not, I actually have a pretty good time. So it's kind of an adventure also. Next slide, please. So when you see one of these, you kind of know what it is, right? And that's because you've seen these a lot of times. But if you hadn't seen this, you wouldn't be able to look at it and know exactly what it was. Next slide. Now take a look at this. Most people think that if we found life on another planet, it would look like that, right? So take a look at this thing and think about how it kind of relates to the thing we just looked at. It's got these two holes in the middle of this kind of circular thing. And it's got this kind of thing here. And maybe those things all have a purpose. And so you begin to look at structures. You look at the symmetry of this thing and you say, oh, maybe that means something. So we don't have to do it with the baby anymore because by now all of us know that we once were a baby, and so we can recognize one. But if we are going to go looking for life somewhere else, we have to have a big picture and a very open mind about what life might look like. Next slide, please. Because life is more likely than not going to look like this. These are microbes. And the reason why we think that life would be more likely to look like this than our little green friend is because, at least on Earth, these types of organisms are the bulk of all the life on Earth. Most of the life on Earth is microbial life. I'm sorry, we're just not that special compared to that. We can do more things, but this is actually some pretty tough life. And in fact, microbial life can live in a much greater variety of environments than we can. We actually have to be coddled a little bit. We can't live where it's too hot or too cold or too much pressure or blah, 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 blah. Picky, picky little humans. Next slide, please. So I told you science has measurements, so we've got to define life in measurable terms. So you could either define life by what it's made out of, or you could define it by what it does. So try to keep this in mind, just as one problem about life. So many different aspects you could try to measure to look for life. But right now, I'm not looking for life. I'm looking for environments that could potentially be habitat for life, meaning environments in which life could be supportive. And that means places that are not too hot, not too cold, not too this, not too that, and especially not too dry. Next slide, please. So life detection, which is looking for life, and habitability assessment are really different. Habitability assessment is more like, I call it real estate assessment. If you went shopping for a new place to live, you'd be trying to figure out if it was livable for you. When I go to another planet to look, and actually I'll be landing on one in 1 month and 27 days, but more about that in a second, I'm trying to figure out what I could measure about it that would make it look like a habitable environment for life. And that's really tough because right now the only life we know about is Earth life, so I have to try to guess what might be a habitable environment for life that was not like Earth life. So it's a really tough problem. Some of the questions we can ask are, what stuff is in that environment? Is there any water? Is there any energy that could be used? What are the raw materials? So these are some of the questions we're going to ask when we land on Mars in 1 month and 27 days, but who's counting? Next slide, please. I'm going to skip this one. And so I wanted to show you a picture of this, not because it's part of the story, but to get back to the adventure part. This thing is really cool. We get to drive it when we're in Antarctica. Actually, we're not supposed to drive it, but I asked the guy if I could drive it, and so I did. And it's got big caterpillar wheels, and that's just to tell you that you've got to have the right tool for the right environment. And I'm going to be talking a lot about tools to use in Mars in just a second, so I wanted you to see that you even have some pretty funky tools on Earth. Next slide, please. Next slide, please. Okay, these are some of those rocks. Remember I told you that they have microbes that breathe metal? So this is just amazing. It's so awesome. And just one little quick digression here. When I went there, they said, okay, you can't drop anything there. I already told you about bringing back your poo with you. So I had some trail mix in the pocket of my parka, and I dropped it. And I thought, I can't leave this here. It's a protected area. So I was picking up all the little, they had things like M&Ms and chocolate chips and nuts. And I picked up this one chocolate chip, and it was really, really hard. And so I spit it out. I looked at it. It was a pebble. I was being so crazy about picking up everything. I actually started picking up rocks and putting them in my mouth. Next slide, please. We'll skip this. That's also Antarctica. Okay, what I really wanted to show you, because this is so cool. So it's very cold there, and you have to sleep in tents. You see that one diamond-shaped tent in the middle, sort of closest to you? Okay, that's the science tent. The next tent in is kind of an orange tent. Can you tell that it's sort of orangey? It's not that great a picture. That's the bathroom tent. And then beyond the bathroom tent, that's the kitchen tent. That's where everybody hung out, because some days it was just so cold there when it was 20 degrees below 0 Celsius. All we could do was sit there huddling around our hot chocolate. But most of the time we were out working on those rocks. Next slide, please. These are some more close-ups of those rocks. I just wanted you to see all the different colors that happen on the surface of the rock when the microbes breathe the metal. What happens over time is that rusty stuff falls off, and then a new layer of bugs takes up residence there. Next slide, please. Now, Mars. So, I'm part of a Mars mission. I've been working on this project for the last 8 years. It's called Mars Science Laboratory. It is a humongous rover. It weighs as much as a car. It's about as big as a car. It has a lot of power, and it has a lot of tools on it, and it's going to Mars to try to understand if Mars is or ever was a habitable environment. And it's going to last for 2 Earth years, which is as long as 1 Mars year. And it's going to rove around. It has a very powerful capability to move a lot of places and make a lot of measurements. I'm not going to read you this, but basically, these are the goals and objectives of our mission. And our mission, should we choose to accept it, is to bring home the information that tells us whether or not Mars could support anything that was alive. Next slide, please. We launched just a couple days after Thanksgiving. It was awesome. The ground shook from so far away. Even though I was standing there jumping up and down, kind of helping it, every time I would land, I could feel the earth shaking until it got high enough up in the sky so that you couldn't feel the ground shaking anymore. It was amazing. And then after it launched, the next thing that we had to worry about was the launch vehicle separating from the spacecraft that's going to go to Mars, which is, in fact, on its way to Mars right now. Next slide, please. I want to show you a little bit about how we're going to make our trip. Can you play the movie? So this movie is the story of our mission, how we get there, how we get into orbit around Mars, and how we land on Mars, and then a little bit about what we're going to do. Okay, so that long tube there, that guy is what gets us there, gets us to space. And so everyone has seen the giant rocket in the picture I just showed you. That drops away after a little while. That gives us a big push. And then we get this thing, and this thing has to separate out from what we call the cruise stage. The cruise stage goes cruising. So now it's cruising to Mars. We've been on our way since November. And we're going to be going into orbit around Mars sometime soon, because we're landing. Your time, if you were on this coast, it would be August 6th. My time, because I'll be in California, is August 5th, so it's late at night. When it gets to Mars, first thing it does is goes into orbit around Mars. And that cruise stage, bye-bye. We don't need it anymore, because now we're going to go around Mars and start to slow down so we can land. So you see there's that orangey kind of cone-shaped thing on it? That's the heat shield. Because when you start hitting atmosphere, even though it's not as thick an atmosphere as ours, it gets really hot. So that thing is supposed to dissipate some of the heat so our precious rover doesn't melt. See, that's supposed to be the flames and stuff as it's aerobraking in the Martian atmosphere. Anybody know what the major gas is in the Martian atmosphere? What? Carbon dioxide. Kind of what you blow into a balloon when you blow it up, right? Because you exhale that. So, oh, we're coming in. So once we get close enough, then a big parachute comes out the back, and that slows us even further. Deploy parachute. Okay, then what happens? We get rid of that other stage that has the heat shield on it, and now we just have what we call our descent stage. With our rover, we get ejected, and now we're going to fly partially down. But wait, there's more. After you get down a certain amount, there are these strings called bridles, and they lower down the rover while the rockets are holding up this descent stage. She's slowly going to begin lowering. Really slowly. Not so slow in terms of how things could go. So as you come down, it's not slow like a feather, but it's slow enough so you don't damage the hardware. See it come lowering down on that? Then there's these little things, kind of like fireworks. We call them pyro shock devices. What's going to happen is when we get low enough, so it's about 15 meters. It's higher than a high diving board at a swimming pool. These little pyro shock devices are going to break apart those cables, leave us there, and the thing flies away, and it crashes about 500 meters, or maybe all the way up to 1 kilometer away, and we're ready to roll on Mars. How cool is that? So after it lands, the next big deal is going to be when we listen for the little beep of the radio to tell us we're alive and well. Okay, we could bail out of this film now and go back to the PowerPoint. So when Curiosity, which is the name of our rover, named by Clara Ma from Kansas City, I believe, we're going to a place on Mars near the equator called Gale Crater. Next slide, please. And it is something that was made by a big impact event. Wham! About 3.2 billion years ago, it made that hole. And then it infilled with a bunch of sediment. And the center kind of rebounds a little bit, and sediment lands on top of it, and you end up with a huge mountain in the middle of sedimentary rock. And our goal is to explore all that sedimentary rock and learn something about Martian history. Next, please. We'll skip this one. Okay, I just want to show you that how every time you do something new, it leads to the next thing that you do new. And that's why it's important to have as many experiences as you can, because you want to keep building on the past ones as you get new ones. So see the tiny little baby rover in the middle? That was Sojourner. When I had my first job at NASA, it was the year after Sojourner went. Then Spirit and Opportunity came. See how much bigger they are? That's the one on your right. That's called the Mars Exploration Rovers. They're still there on Mars. And then Curiosity, that thing is humongous. And that's where my experiment is. Next slide, please. So don't look at all the writing on this. Just kind of get the big picture that there's a boatload of stuff on this rover. And this stuff all works together to measure things about the environment that would help us predict whether or not Mars might have been habitable at one time. The instrument that we work on is an instrument affectionately known as SAM. We think she's a girl, so it's probably actually a shortening of Samantha. Anyway, it stands for Sample Analysis at Mars. Could I have the next slide, please? Sample Analysis at Mars is actually a trio of instruments that can do amazing stuff. Next slide, please. It actually can suck in the air and tell you what the Martian atmosphere is made out of. It can actually raise up a trapdoor, take in some dirt that the drill is going to deliver, or powdered rock that's going to be delivered, and we can measure the gases that get evolved from that solid sample when you bake it really hot to 1,000 degrees centigrade. And then when we measure these gases, we'll know what the Martian stuff is made out of. Next slide, please. And so I told you, actually, to be a little more precise, since I am a scientist and all, 1 month and 27 days and a few hours. We actually are going to land at about 10:37 p.m. Pacific Daylight Time. But all during the time that we're doing science on Mars, we're going to actually be on Mars time and trying to set our watches to whether it's daytime at Gale Crater on Mars. Next slide, please. So I want to teach you something really, really important. Remember I said before you got to have a big picture and keep a really open mind about stuff? Remember that part? Let's have the next slide, please. So when I was in graduate school, one of the many times, I studied a topic called petrology. And petrology tells you how rocks get formed. What is the genesis, the formation of rocks? And a certain type of rocks you study by looking at very, very thin slices of it under the microscope. And one famous guy that wrote a textbook drew lots of pictures of what these microscope slides look like. And a friend of mine told me a couple of years after I graduated, did you see the little self-portraits in the microscope slides? And I said, no, what are you talking about? And he said, well, the author of this book, McBurney, had kind of a sense of humor. And every time he drew a microscope slide, he had a little drawing of himself in the microscope slide. So I whipped out the book and I started looking at all these pictures. Next slide, please. And what do you know? Every single page where there were these drawings, there's a little bald guy smoking a pipe. And the moral of that story is, if you're not looking for the guy with the pipe, you're not going to find him. So you have to keep a very open mind. You have to look for everything, because sometimes we only look for what we expect to see. And the right way to be an explorer is to keep an open mind. Next slide, please. So I hope you're ready to join me in exploration, whether it's on this planet or whether it's on some other planet like Mars. It's really a lot of fun. So ask yourself a couple of things. How good are you? Are you willing to work hard and be really good at it? How good are your friends? I remember when I was Girl Scout, my patrol was called, oddly enough, the Jetsons. We were the best at making corn muffins. Why were we the best at making corn muffins? Because we loved corn muffins and we wanted to eat them. How committed are you? How good you are at anything you do, whether it's being a good person, whether it's being a good Girl Scout, or whether it's being a good daughter, or maybe it's being a good explorer, is a function of how committed you are. Notice that luck is not on that list. It's not luck. It doesn't matter what you were born with. What matters is how hard you try. So figure out what you want to be, try really hard, and make it happen. And with that, I'll stop and take a couple of questions. What will we be doing in California? So after the spacecraft lands, for the first 3 months, we all have to learn to work together. There are hundreds of us on the same team. So we'll be at the NASA Jet Propulsion Laboratory in Pasadena, California, the night it lands. And as soon as the rover touches down, we'll begin planning surface operations. And then after 90 days, we'll all come back to our home institutions. Mine is in Greenbelt. And then we'll continue to operate the spacecraft for at least 2 years.
Do you think we're more likely to find life like with a Curiosity rover that finds microbes, or with aliens who have been getting our steady radio signals and decide to send back some of their own TV?
So that's a really good question. It's what kind of life are we more likely to find than other kinds of life? So some of you know this program called SETI, which is the Search for Extraterrestrial Intelligence. So in my opinion, we're just as likely to find no life as to find life. Personally, I think there's life on other planets. Will we find life on Mars? I don't know. Our particular mission is not made to look specifically for life. Our mission is designed to understand the planet. And the reason for that is because we don't know how to define life in other places exactly yet. So we think we have some ideas about how we recognize intelligent life here. Although, you know, when I'm really tired, probably people could look at me and say, not so much. But we don't really know what intelligent life looks like somewhere else. we think we might know what microbial life looks like on Earth. We don't know what it looks like somewhere else. So we don't really have a good idea what life looks like, but we have a great idea what the other stuff looks like, because from observational astronomy, we know they have minerals on every asteroid, on every planet, and stuff like that. So I don't know which life we'll find first. I hope we find life somewhere else. Obviously, I'm an astrobiologist, but your guess is as good as mine, and we could use plenty of helpers, so if you're interested. Yes?
What sort of stuff did you study in college to get you where you are today?
So I am not your typical scientist. I majored in music, and I got a degree in opera, and I was an opera singer for a while. And then I got another degree in composing, and I was writing film scores and jingles and things like that. But I always loved science, and in fact, I got a science fair prize from NASA when I was 14, a little medal, which I still carry with me in my pocket when I go on expeditions. And I didn't major in science because my 8th grade math teacher, Mrs. Heinze, told me I was stupid. So, lesson 1, if somebody tells you you're stupid, don't listen, or you'll end up majoring in music, which in itself isn't so bad because I can play a lot of instruments. But I did go back to college after I got my bachelor's and my master's degree, and then I got a PhD in mineral physics. So to be an astrobiologist, you need a really broad education in all the sciences. So I recommend chemistry, biology, physics, math, systems engineering. Everything that you can study will help you learn about everything else you will ever learn in your entire life.
Do you think you'll be able to make an estimate for how long it'll be until we find intelligent life in space?
How long will it be until we find intelligent life in space? Wow, I have absolutely no clue. Since a number of you are thinking about intelligent life, I'm guessing some of you have heard about something called the Drake equation. Who's heard of that? Raise your hand. Oh, we got a few people. So the Drake equation is an equation that was developed to help us predict how many intelligent species there might be out there. And the thing is, while there could be, as Carl Sagan so famously said, billions and billions, I don't know, because it's just a statistical prediction. So how likely we have the statistical equation, but it doesn't have measurable terms in it. So until we can get a little bit more refined at our statistical prediction, I have no clue. Do I think they're out there? Absolutely. How many of them? No clue. How soon do we find them? Also no clue. Sorry? Yes?
Do the rovers ever come back to Earth, or do they just stay like on different planets forever?
Sadly, it is a one-way mission. So the 3 rovers that have gone to Mars are there for good. The 4th, my rover, Curiosity, also will be there for good. We are working on what we call an architecture, a plan for a series of missions to, at some point, bring back samples from Mars, but those will only be rock samples. They won't be the spacecraft that we bring there. So as humans, we're kind of untidy. We leave our cars out on the other planets and we don't garage them. But at some point in the future, when we learn how to bring back reusable things from other planets like we do from the space station, then we'll be able to do that. Oh yeah, a lot of people are working on that. They are way smarter than I am, though. So if that's something you're interested in, those engineers could use some help, too.
Thank you so much, Dr. Conrad, for speaking with us.
My pleasure. Awesome.
We
so many of them. Where do I get the green pennies? Where do I get the green tennis shoes? We have flyers. You can get them online.
Thank you so much. We hope you enjoyed hearing from a scientist at NASA Goddard Space Flight Center. So now we have our last speaker. So I have to ask the question: how many of you dream that you could go into space? I know I do. Yeah, so we have a really special speaker here. She is a former astronaut. She piloted 2 missions, and she was commander, only the second female to command the space shuttle at that time. And so that was her 3rd flight. She is now the senior technical advisor for the FAA's Commercial Space Transportation Group. And today we have Lieutenant Pam Melroy, Colonel Pam Melroy. Thank you so much.
Thank you. Thank you. It's great to be here. Say a big hello to everybody who's all the Girl Scouts who are watching. I was a Girl Scout, and I think probably the most important thing I learned as a Girl Scout, which is extremely useful for astronauts, is to be prepared. So that's a very important part. And as I talk a little bit about getting ready to fly in space and flying in space, you'll see why being prepared is really helpful. So I'd like to start out with my slides, if we can pull up my first slide. Got a PowerPoint somewhere here. I also have a home video to show. Hope you'll enjoy that too. Let's, okay, I'm going to talk a little bit about human spaceflight today. You just heard about our exploration of the solar system, and I'm going to finish up by talking about the exploration of the solar system. But I'm going to start out with talking about my generation of astronauts and what we have been doing. And then I'm going to go on and talk about what your generation of astronauts will be doing. One of the most interesting things about being an astronaut is that people have sort of this feeling like you were born an astronaut. They can't imagine that you weren't always an astronaut. Next slide, please. Well, I always like to show this picture of myself as a little girl. I'd stolen my father's Air Force flight cap, and my mother caught me in the garden impersonating an Air Force officer, which is a crime. She didn't punish me. In fact, what my parents did was they always encouraged and told me I could do anything that I wanted to do. And so I was really fascinated with the sky. I think my parents thought that I might be a doctor or a lawyer, but I decided to become a test pilot and an astronaut. Because when I was your age, the only astronauts I'd ever heard of were military jet test pilots. But it turned out that I fell in love with flying, and I loved being a test pilot because you get to do experiments with airplanes. And so it was a wonderful experience to try to become an astronaut by being a military pilot. Next chart. But what I didn't know when I was a little girl was that there was another little girl out there. So I was only the 2nd woman to command the space shuttle. And I was sure that I was going to be a commander someday. There was no doubt in my mind I was going to be the commander of a spacecraft. But this other little girl who grew up on a farm in Iowa was dreaming the same dream. Next slide, please. And we never guessed that the 2 of us would be commanding a spacecraft at the same time together. Peggy Whitson commanding the International Space Station at the same time I was commanding the space shuttle. It was an historic moment. It happened just by accident. There were just enough women astronauts in the Corps to allow this to happen. Next chart, please. And of course, shortly after our flight, another historic first, 4 women in space at the same time. So we hope those numbers will go up when you get flying. Next chart. So I'm going to talk a little bit about the missions of the space shuttle, which is my generation of astronauts' vehicle into space. Next chart, please. So the space shuttle, when it was first designed, did a lot of missions to carry satellites up into space. So satellites such as the Hubble Space Telescope, a very famous satellite that's up there observing the wonders of the universe. And we could go back, we could service it, we could visit it. And you saw a lot of the early missions of the space shuttle were about doing that. Next chart, please. But in fact, space offers something very unique, which is microgravity. So there's no such thing really as zero gravity. You have to follow gravity. It's the law. But in space, around in low Earth orbit, all the forces balance out, and you have what feels like a net zero gravity, or what we prefer to call microgravity. every experiment that we have ever run here on Earth can be run again in space with gravity gone. And that's a really amazing change, something different to see. You see my friend Koichi Wakata showing that in space, the primary force that's acting on fluids is surface tension. So when fluids don't run down like they do in gravity, they glom together into a little ball. And so we started to do science aboard the space shuttle. There was a problem, though. Doing science only about 7 times a year for about 10 days at a time made us come up with the idea of doing science 24/7 in space. And that's how the idea of the International Space Station was born. Next chart. So this is the way the International Space Station was dreamed of before the very first piece of hardware was ever launched. Take a good look at it. I'm going to show you a picture of the way the station looks now, and you can decide if it looks pretty close to the same. You can see that there is a long section down going across from left to right. That's called the truss. And it's not a living quarters. It's an engineering word. As a truss, it holds things. And in this case, it's holding the solar arrays. The solar arrays are a very important part of the space station because you have to get electricity to the space station, and 250 miles up is way too long for an extension cord. So you have to have power, not just to keep humans alive, but when you're in the laboratory, one of the things you see everywhere is computers and power outlets to plug in your experiments. And that's what the solar arrays do. They gather the rays of the sun, convert it to electricity, and they provide that for doing science aboard the space station. It's almost a little hard to see the living quarters or the pressurized area of the station. It's down the middle, and that's about the size of a 5-bedroom house, pressurized volume. And at the end facing us is the business end. That's where all the laboratories are, the US laboratory, the Japanese laboratory, and the European laboratory. Next chart, please. So my generation of astronauts has been building the space station until the end of the shuttle era. And this is the way the space station looked on each of my 3 visits. On my very first visit, just a couple of elements. There was no one living aboard the space station. It was a little bit like going into a hotel room. We kind of spread out, we hung out and had a good time. But on my second visit, there were people living there. And we had to be respectful of that because they were doing their science every day. And you can see how much bigger the space station got on each visit. Next chart. So I'm going to talk a little bit about my last flight in space because we had a pretty good story to tell that I'd like to share with you. This was in October of 2007, the STS-120 mission. And next chart, please. I'd like to introduce you to my crew. That's me in the middle. And starting from the left, Dr. Scott Parazynski, our lead spacewalker. He was on his 5th mission in space. So his job was to orchestrate all the spacewalks. And right behind him, Doug Wheelock, an Army helicopter pilot who was on his first mission, spacewalking also with Scott. Next is Stephanie Wilson, an aerospace engineer on her 2nd mission in space. So if Scott was my right-hand guy for spacewalks, she was my left-hand gal for robotics. Robotics are very, very, very important in space, especially during the construction of the space station. Sometimes Stephanie would operate the robot arm on the space shuttle, put the brakes on, float over to the space station, and then operate that arm and go back and forth. She was a busy lady. Between Stephanie and I, George Zamka, on his first mission, he was my pilot. So one of the responsibilities that I had as a commander was not just to execute the mission, but also to help prepare and train George to be a commander on his next flight. Next to me on the other side, Dan Tawney, who was on his 2nd trip to space. Dan had an interesting position on the crew. He wore 2 hats. He was my crew member. He helped Stephanie with robotics, went on one spacewalk with Scott, but we left him aboard the space station where he became Peggy Whitson's crew member, and then we took Clay Anderson, who'd been on the station, back home to his family. And finally, at the end, Paolo Nespoli, a European Space Agency astronaut on his first mission from Milan, Italy. Next chart. So our primary purpose was to deliver Node 2, which was the hub of all of the international laboratories. So it's kind of like the hub on a Tinker Toy set where all the international labs attach to it. And you can see that it fills up about half of the payload bay of the shuttle. It was quite heavy, weighed a little bit more than 30,000 pounds. Next chart. We had another responsibility, though. Early in the formation, in the construction of the space station, we had just a single solar array. And this was before the truss had been built. So at the beginning, it sat like a hat on top of the living quarters. You can kind of see that up in the top left-hand corner. It's circled in red. Well, when the truss was completed, it was time to furl that up. And that's what the crew before us did. You can see it circled in red on the right. And our job was to use a combination of the robotic arm and spacewalkers to detach it, move it out to the end, and unfurl it like you see in the bottom picture. So we had two responsibilities, the node and relocating a solar array. Next chart. How do you get ready? Well, just like I told you before, be prepared. That's very, very important. We spend a lot of time in the simulator practicing all the scenarios, not just the things we know we're going to do, but if there's anything that goes wrong, because after all, we're explorers, and sometimes there are surprises. So we would practice in the shuttle cockpit, everything from launch to entry to docking to the space station, and we had instructors who would help give us failure scenarios. They were like our teachers, and they helped us to understand the systems better. Next chart. As a pilot, I only got to land the space shuttle every few years. So in order to stay proficient or practiced as a pilot, I flew these little supersonic aircraft called T-38. The pilot astronauts sit in the front, and the scientist astronauts sit in the back seat. Next chart. I mentioned the robot arm earlier. I'd like to point out, if you could look at the picture on the left, the space shuttle robot arm. It's a lot like a human arm. It's attached at the shoulder, and it rotates at the shoulder, the elbow, and the wrist, and it can hold on to things. And in this case, what it's holding on to is a long pole or a boom. And it's a part of the robotic system that we wave around. It's got a camera on the end of it, so we can look at the space shuttle after liftoff to make sure that we took no damage. Now, if you want to refer to the shuttle arm like a human arm, you go over to the space station arm, which you can see hanging in a V on the bottom of the picture on the right. If you want to try to compare that to a human arm, it would be double jointed because it swings all the way around, and it can go in any axis like that. The other interesting thing about that arm is that it can grab at both ends. The space station is much bigger than the space shuttle. It's about the size of a football field in all three dimensions. So we realized pretty early on we couldn't have just one arm. It would have to be too long. So what we decided to do instead was to allow it to detach itself and literally walk around the station to get to the place that it needed to be. Both of these arms were built by Canada, Canadarm1 and Canadarm2, their contribution to the space program. Next chart. And of course, we try to use the robot arm as much as possible because it's the safest way to be inside the spacecraft, moving big things around using the robot arm. But unfortunately, you can't do everything that way. And just because you've added a new piece to the space station, it's like adding a new piece to your house. It doesn't mean you're actually ready to move in yet. You have to have electricity. You might have to have telephone connections or data if you want to set up a computer, air conditioning and heating. And so we send our spacewalkers out to make those connections, to make that element ready to live in. And these guys go out with the biggest cordless drill you have ever seen in your life and a bunch of other tools, and they bolt things together and make those connections. Next chart. We have another thing that we do in space that's very different, and that is we live together in a very small space, about the size of a minivan, all 7 of us camping out. Now, that's really different, because here at work or at school, you go home at the end of the day to your family, but in space, that doesn't happen. and your lives depend on each other. Whether you're doing robotics or whether you're sleeping, anything can happen. And so how do you practice for this? Next chart. You go camping. That's the best way to practice and train. So I took the crew through the National Outdoor Leadership School program, sea kayaking in Alaska for 10 days. So every day we filled up our kayaks as full as they could go and paddled anywhere from 15, 20 miles every day. Next chart, please. At the end of the day, we'd unpack. We'd have to set up our tents and our sleeping bags. We'd have to cook dinner. And then we would talk. We would talk about how the day went and how decisions were made and what we should do the next day. And believe me, after 10 days of this, you know everything there is to know about your crewmates. Like who gets really cranky when they're tired, who gets really cranky if she's not fed 3 times a day. Those are important things to know about each other. So we become a family. Next chart. And that is the purpose. And in fact, I found myself reflecting as I thought about the Girl Scout promise and the law, how many of those promises to be helpful, to be respectful, to consider resources are exactly the same kind of thing that makes a good crew member in space. So I consider you astronauts in training already. Next chart, please. I do want to point out that there is another part of our team that doesn't show up in any of the pictures from space, and that's our families. This is my family portrait. In the middle in red is my husband, Doug. On the left, my son, Ryan. On the right, my stepson, Reed. And I am just outside the top of the picture there, launching in the space shuttle. Next chart. So we had a good flight. We had a good mission. Everything was going extremely well. We launched. We docked to the space station. We got Node 2 lifted out of the payload bay and attached to the space station. We did 3 fantastic spacewalks, all kinds of interesting things. Things were going smoothly. We got the solar array detached. We got it moved out to the end. And then Peggy and Dan and I went to unfurl the solar array. So the first half went out perfectly. But the second half, next chart, please. We were about 2/3 of the way through when this is what I saw through the cameras. And I thought, I don't think this looks right. So I called for an abort, and then we all floated over to the space shuttle and looked out the window with our binoculars. Next chart, please. And to our horror, we saw this tear in the solar array. There's actually 2 tears in the solar array. There's a smaller one on the right. So what had happened was some of the cables that are used to provide tension had caught in some of the cables that go across, because it kind of folds up like an accordion. So when it was unfolding, they got snarled and began to rip the solar array. This was a very serious problem for the space station. We needed the power of those solar arrays for the Japanese laboratory and the European laboratory sitting on the ground in Florida, ready to launch on the next 2 missions. We needed the power. We had to have it. So you say, okay, go out and fix it. Right, except we had another problem. The solar arrays are always electrified, 120 volts DC, which will give you a nasty shock and burn out all your electrical systems. So you can't touch it. And in fact, we told our spacewalkers never to get near the solar arrays because we didn't want to take any of those chances. We had no way to get a spacewalker all the way out there. This was the outboard solar array, mostly deployed. The robot arm of the space station, even at the farthest end, was not long enough to reach. And then once you got out there, what were you going to do anyway? Well, this is NASA. Failure is not an option. Next chart. Just like on Apollo 13, the people on the ground dumped a box, this time with everything aboard the space shuttle and the space station, and said, what can we do to solve this problem? So we had 3 different pieces to the problem. First, the guys on the ground had to look at the solar array and come up with a way to stitch it up. It needed to have structural strength so that we could deploy it. If we could not do that, when we fired the thrusters of the shuttle to back away from the space station, we're going to cause the solar array to tear, possibly some of those electrified cables to break, and we would have to jettison the solar array and not be able to launch the European and Japanese laboratories. We had to fix the solar array, or we were going to have to jettison it. So once we decided how to fix it, we had to construct something. And so you see Peggy and George here constructing a repair. And then finally, we had to figure out a way to get people out there, and that was the job of the robotics team. Next chart. This was the repair that the folks on the ground came up with. To stitch it up, they came up with the idea that we would have sort of a what we called a cuff link. So using electrical conducted wire with a flipper bar on the end, because there were these holes built into the solar array as a part of the design and manufacturing process. And so you could poke that flipper bar through the hole, and then it would flip and then lock into place just like a cuff link. So the idea was to put 5 of these across the solar array in place so that when we pulled it tight, it would have structural strength. Next chart. And how could we get someone out there? Well, we came up with an idea. Remember I showed you back when the space station robotic arm, and it was holding on to that boom? Well, that belongs to the space shuttle system. It's really not meant to interface with the space station arm, but guess what? It physically could. There was actually a place to grab it right in the middle. And what you see there is the space station arm grabbing a hold of that boom. There's a camera at one end, and at the other end is Dr. Scott Parazynski, who is about 6'4". So that should give you an idea of how huge the arm is. That's him out there at the end, standing on a little 3-foot extension and a footstool. Next chart. So there is Scott stitching up the solar array at the far right. You can see that we had to kind of wind our way from the inner solar array to make sure we didn't touch it. At no time were we allowed to have the arm or anything on Scott's suit touch the solar array, and he wasn't allowed to touch it. He could poke things through it, but he couldn't actually touch it with any part of his suit or his gloves or anything like that. At the other end, which you can barely see, at the base of the solar array was Doug Wheelock, the other spacewalker, and he was watching Scott very carefully. And it's a good thing that he did, because we had never practiced this before. We weren't even sure Scott could do it. We weren't even sure that the arm would reach. So there were a few surprises. When Scott went, next chart please, when Scott went to, this is the view from Doug's helmet camera, after Scott had already backed away from the solar array. When he was stitching, he was much closer to the solar array. So as Scott went to put the first cuff link in, he did what seems perfectly logical. He inserted the flipper bar, locked it into place, and then what? Gave it a little tug just to make sure it was in place. Well, this is microgravity. And what happened when he gave a tug was that the billow went all the way down to the bottom. Now, I was looking out the shuttle straight at Scott, and I couldn't see this. But Doug, who was at the base of the solar array, saw the ripple come down, and then to his horror, he saw it going back up. A big billow coming right at Scott. So he called, "Scott, look out." Scott's like, "Look out? What's out here?" And he looked down, and he saw it coming, and he realized what was going to happen. So he had a tool that was covered with insulated tape. So he leaned back as far as he could in the step stool and held the tool out in front of him. So the billow came up, and it kind of got messed up with him holding the solar array, and it kind of wobbled, and the whole solar array went like this. And then after a little while, it kind of settled down again. And we all went, phew. And then he had to go do it 9 more times, which just tells you what you can get used to if you have to. Next chart. I'm happy to say that we deployed the solar array fully. The stitches worked. They are still in place. I know exactly where to look whenever anybody from our crew goes up to space, as they have subsequently from this mission. We always take pictures and send it down to everybody. Looks like it's working. And in fact, the solar array is producing 99% of its design power. Next chart. So this is the way the space station looks today. Remember the picture that I showed you earlier? Well, there it is. You got a truss, you got all the laboratories, you got the 4 solar arrays, looking pretty good for a design that we came up with that we'd never tried to do something so difficult before. Next chart. Can we run to the DVD, please? I'd just like to kind of, now that I've told you the story, the video really kind of helps you understand it even better. Let's just go to space together. Does that sound like fun? Everybody up for that? Okay. So it's a home video. I talk about that because we actually don't have professional photographers in space. So here we are walking out to the launch pad. And do we have audio? Can we get audio? There we go. Start. And a view of the engine starting and a camera pointing down at the pad. And then in the upper right, a view from inside the cockpit. That's me in the front left seat. So let's get a little more audio. Can we get a little more audio? There we go. We're rolling to get into the correct inclination orbit to catch the space station right off the pad. So after 2.5 minutes, the solid rocket boosters separate. In the lower right-hand corner and on the left side, you'll see the space shuttle fly away from those solid rocket boosters, but still carrying that orange tank, which is our liquid rocket fuel. So those solid rocket boosters fall back down into the ocean and are recycled and reused. After 8.5 minutes, we're in space. We separate from that orange tank, and it burns up in the Earth's atmosphere. So after a couple of days of preparation in space, we approached the space station. At about 600 feet, I stopped and put the shuttle into a backflip, not because I was showing off, but because we could take pictures of the space shuttle. Here I'll invite you on board for the moment of docking, the station and the shuttle.
Discovery and Alpha, capture confirmed.
You can see the whole crew.
And ISS is in free drift.
Houston copies.
Fist bump, yeah. And the ship's bell.
Discovery arriving.
Based on naval ship tradition, there's a ship's bell. And, of course, Peggy and I shaking hands through the hatch, and everybody's saying hello. There's a ship's bell on the space station they use to welcome us. Unfortunately, there's not a whole lot of time for the hugs and kisses. We're always really happy to see each other, but we had to get to work right away. You can see Dan and Stephanie lifting Node 2 out of the payload bay of the shuttle using the space station arm. This is greatly sped up, of course. As they're lifting it up, it's nice and slow and gradual because it's big and heavy. You don't want to wave it around too fast. Pull it out of the bay, slide it out over the sill, and then flip it into the right configuration to attach to the space station. And it was an exciting moment to open the hatch and get to go inside a new room for the space station. Bright, clean, shiny, and great for doing backflips in. Here the guys are back at work, unbolting the solar array, rebolting it, making all those connections on the node. As we started to deploy the solar array, first half went fine, bad news, and the drama ensued. And so you'll see here in the upper left, Peggy and George making the cufflinks. On the right-hand side, spacewalkers with my help getting ready for the spacewalk, and then, of course, finally the robotics team. This is the view from Doug's helmet camera. You can see how floppy that solar array is as Scott slides the first cufflink in and puts it into place. Good thing Scott has a background as an emergency medical doctor. He did a fine job stitching up the patient. And then, of course, the solar array very gently deploying to full deflection. Take you on a quick tour of the space station here. That's the closet right there. I think everybody's got a closet like that where stuff doesn't all quite fit in the corners. Going through the business end of the space station, this is the Destiny Laboratory. One of the things you notice right away is that in microgravity, you can put experiments and other equipment on the ceiling, on the walls, or the floor. There is no up or down. It doesn't matter. You can take advantage of all of the space. And, of course, the best part is looking at the Earth. These are some wildfires in Southern California that we were the first to get pictures of. Just an amazing sight. All good things have to come to an end. This was quite a mission. I don't think I need to tell you that. We had to stay in space several extra days, very close with Peggy and her crew. Clay Anderson coming home after 5 months in space. One last fist bump, and then it was time to undock and come home. Saying goodbye to the space station is a really hard thing to do, but it's amazing to see it grow before your very eyes. Coming back in through the Earth's atmosphere, the shuttle is the world's biggest glider. The distinctive double boom that you hear, the vehicle is large enough that you hear the leading and the trailing edge shock wave. As you approach the runway, diving like a brick, coming in about 7 times as steep as an airliner, at about 15 seconds before touchdown, George put the gear down. I landed. We're going about 1.5 times faster than an airliner, so we deploy a drag chute to help slow us down. So the space shuttle is an amazing vehicle because it can be an orbiting laboratory, a rocket ship, and it can come back like an aircraft. So can we go back to the charts? There we go. Future of the International Space Station. So let me talk about the future now, because the space station is built and it's producing science, that vision of 24-hour-a-day science. It's going on right now. Next chart. And one of the best parts about it is that this is about partnership around the world. Unlike earlier parts of the space program, which were based on competition, this is based on cooperation with other countries. Peaceful cooperation, doing science together. Next chart. But without the space shuttle, how do we get things up there? Well, right now there are 3 vehicles, the Russian Progress, the European Space Agency ATV, and the Japanese HTV, that carry cargo up and bring trash down. I'm going to have to update my charts. Next chart, please, because now there is a 4th. What happened was several years ago, NASA realized that the aerospace industry in the United States was strong enough that a private company could figure out how to do this. What do I mean by that? Well, there's a big difference between a NASA vehicle and a commercial vehicle. It's a little bit like calling FedEx and say, would you please deliver my package to the space station for me? And that's exactly what they did. The very first commercial company, SpaceX, delivered the first packages to the International Space Station just about 2 weeks ago. So an amazing event. And there's another company that's about to do it later this year. So this is a tremendous capability for us. It's really a renaissance for space in the United States to have the commercial industry pick up this capability. Next chart. How do we get humans up and down? We've talked about cargo. Well, right now, we're using the Russian Soyuz. This is a rocket that's been around for a long, long time, taking crews up to space and back, very safe, very robust. But we would like to have the capability here in the United States as well. Next chart. And so there's a new program called the Commercial Crew Program. So there are several companies who are actively building up the capability to develop essentially a space liner, a commercial company to take astronauts to and from the space station. So neat idea. Hopefully we'll see it come true in about 4 or 5 years. Next chart. I do want to take a moment to talk about commercial space transportation because that's what I'm doing now since I left NASA. I'm working on all these vehicles that are growing, the suborbital vehicles, orbital vehicles like the ones that go to the space station. We provided a license for the commercial mission to the space station. Next chart, please. And there's some very exciting and interesting things that we think are going to happen in commercial space. You're going to be able to buy a ticket to go to space, whether it be for 5 minutes or 5 days at some point in the future. The 5 minutes one is coming a lot sooner, within about a year. But we think there's other exciting opportunities too. Imagine point-to-point suborbital transportation. What am I talking about? I'm talking about Los Angeles to New York in about 30 minutes. That's what suborbital can do for us. So someday we hope to have that capability. That's still a ways out there, but we're seeing that capability growing. Next chart. Well, let's go back to NASA for a minute, because NASA wants to have these commercial companies take care of the International Space Station. Why? So they can explore the rest of the solar system. Next chart. So the vehicle that NASA is currently designing to go outside low Earth orbit. Now remember, the last time we sent a human outside low Earth orbit was in 1972, when we sent the last crew of Apollo to the moon. We have not been outside low Earth orbit with a human being since 1972. So this vehicle, Orion, is the vehicle that's being designed to have the capability to do that. I've had a lot of people look at it and say, well, gosh, you know, it's got like a capsule and a service module and a launch abort system. That kind of looks like Apollo, right? Well, there's a big difference. And the best way I can describe the difference is by comparing Apollo to Kon-Tiki. If you're familiar, there was a Norwegian explorer called Thor Heyerdahl who wanted to prove that it was possible using primitive tools and capabilities to build a raft and cross the ocean. And that raft was called Kon-Tiki, and he was successful. Apollo was like Kon-Tiki, very, very primitive technology in the 60s. The computer that got us to the moon had a 32 kilobyte memory capability, which is, most of us write emails bigger than that now. So it was very primitive technology. We proved we could get to the moon, we could get back. If you want to compare Apollo to Kon-Tiki, compare Orion to the Mayflower, because Orion has the capability to loiter in lunar orbit or go out even further and be gone on voyages of 6 months or beyond. So it is about going and staying. It's not about just proving you can do it. It's taking the next step. Next chart. It's very exciting. There's already been the first flight test, and the ground test article is built. The second flight test is set for 2014, and hopefully we'll see humans riding Orion by 2017. Next chart. The thing I want to point out about going outside low Earth orbit, trying to clarify that, is that we think low Earth orbit, we do understand how to do it, and that's why we feel our industry is prepared to do it. But if you're going outside low Earth orbit, it's a much more challenging problem. You have to protect from radiation. It's a much higher speed of entry coming back into the Earth's atmosphere. So you have to have a bigger heat shield, and also stronger structure to support it. So this is really right for NASA to be working on this and let the commercial companies go to the space station. Next chart. But what's the real future of exploration? What's your future? Next chart. Well, we've heard a lot about rovers today. That was a terrific presentation right before this that we heard about Curiosity. Of course, this is the Mars exploration rover, Spirit and Opportunity. We send these rovers to study what Mars looks like. Next chart. So we take a look. We try to study the chemical composition, the geology, the atmosphere, all these things. I mean, stop and think about it for a minute, okay? Mars is a big place. So imagine if you were a Martian. Imagine you're a Martian and you live on Mars and you want to study Earth. Where would you go on Earth? Would you go to Antarctica? Or would you go to the Alps? Would you go to the beach? Where would you go? Well, we send these rovers so that we can figure out where to go. Next chart. So that ultimately we can send a rover 10 times as big carrying one of you. The first people to go to Mars in about 20 to 25 years are in school today, between about 5 and 25 years old, and it could be you. So I hope to be back here in 25 years to listen to your talk about your trip to Mars. I think that's all we've got time for today, so thank you very much.
Thank you so much, Pam, for speaking to us. It was a great talk, and you learned about what we did in the past, and you've learned about what we're planning to do in the future and what we're doing currently with the International Space Station. So thank you so much for that talk. Well, Girl Scouts, that is the end of our program. We are so glad that you're able to join us. We wish you the best time tomorrow as you rock the mall to celebrate your 100 years and your sing-along. Thank you so much. And if you want to stick around, Pam will entertain some questions, so you are welcome.